Swayam Prabha. Digital India. Educated India.
Good morning everybody. Today we will be discussing another interesting application of vacuum technology in very important application, that is analytical instruments. I need not emphasize the importance of analytical instruments in day to day life, because most of the products that we will be using in our life, whether it is chemicals or pharmaceuticals or any other materials, even metallurgical appliances, everything, while they are being manufactured, they are finally analyzed before they are sent to the market, okay, including biotechnology products, medical appliances, everywhere, okay, even pharmaceuticals and food products even. So, everything requires analysis. You are producing something, whether what is its physics, what is its chemistry, what is the risk of using that, how can you analyze it unless you know something about its structure, about its chemistry, arrangement of atoms inside at a microscopic level. So, it is this that is being explored in the last century by several scientists in developing several modern equipment, which are popularly known as analytical instruments. And these analytical instruments are invariably having a vacuum environment. There will be vacuum chamber, vacuum pumps and variety of vacuum gauges, etc. In addition to electrical equipment and data acquisition, etc. But finally, the materials being processed are always under vacuum. Even the method by which you are analyzing either bulk form or its surface form or interface form of various materials, that method also wants vacuum for its operation. So, all that we will see in this lecture in a brief manner. The concepts that are going to be covered are scanning electron microscope, transmission electron microscope, energy dispersive analysis of X-rays, X-ray photoelectron spectroscopy, X-ray diffraction, atomic force microscopy, and then finally mass spectrometry. We will give some introduction and conclusions also. So, to introduce the subject to you, basically what I want you to appreciate is any material, too big it may be, big structural material like bridge or anything. To start with, it starts with materials. You have to use some materials, and these materials, when they are made, whether it is metals or alloys or ceramics or pharmaceuticals or chemicals or powders or liquids, they must have analyzed its physics and chemistry in the starting point using some analytical instruments. That is why we can say that analytical instruments are essential tools for research and production in various domains like advanced material research, nanotechnology, nanometallurgy, medical applications, biotechnology, ceramic engineering, pharmaceutical industries, food processing and semiconductor technologies, IC chip manufacturing, etc. In the last century, there was a lot of scientific activity over this, because you are making varieties of products, but you do not know whether they are of good quality or not. So, there was a heavy demand parallelly to develop these instruments. Even now, they are continuously being upgraded with better and better resolution. So, what are these instruments? As I already told you, EDAX, SEM, TEM, XPS, XRD, AFM, they are mostly known in the short form, but I have given long form also. You can read and memorize, that is very important. What is the role of all this? Just now I have told you, to understand the physics and chemistry of materials, based on which you develop different technologies, that is all. This is a microscopic picturization of macroscopic property measurements. Okay. They are related to microscopic structures, physics and chemistry. If it is a topography, it is physical structure. If it is a chemical analysis, it is a chemistry of it. Both of them have to be analyzed. That is why these instruments are called analytical instruments. They analyze something, okay. And sometimes they give beautiful images at a scale which normal eye cannot see, okay. And lots of safety precautions you have to take. But luckily, most of these instruments are related to vacuum. So, the entire instrumentation and the sample, everything is inside vacuum. So, we have to only remotely control everything, and using instrumentation we have to get some useful information. Okay. So, high vacuum pumps are essential requirement, otherwise you will not get any meaningful information about either material or process. Sometimes these instruments are used along with a process, while process is going on continuously, it is getting monitored as a quality control. There also these analytical instruments are used. And in some solid state technology, etc., the material with which later we prepare some large scale useful equipment, like even computers, etc. You have to analyze to start with initially in a microscope. I am repeating these things again and again, because I want you to now come to the domain of instrumentation, analytical instrumentation for advanced materials used in different branches of science and technology for welfare of human race. And everything is related to vacuum technology, because that gives clean and green environment. So, that what we measure is a virgin information, we are not measuring some impurities falling on it. And standard UHV chambers, CF flanges, which you have covered in the first 35 lectures, you can go through that, all of them will be again used here, and with reduced outgassing and with minimum leak rate. These have to be there. So, the first instrument that we will be covering is scanning electron microscope. Okay. It is an analytical method. It is useful for analyzing crystalline materials, microscopic organisms, etc., and it is used in several industries for surface composition of their components and products. It can be a semiconductor industry or advanced materials manufacturing, or food monitoring, or a pharmaceutical industry, or medical devices, or microelectronics, or nanotechnology, or nanomaterials. Okay. Advanced metallurgy, for example, ceramics, all these industries, they use this scanning electron microscopy. Scanning electron microscopy is a very, very useful equipment, and it is being regularly used in almost every industry or every academic organization. I would say every laboratory, they will have one scanning electron microscope. The cost of it is also coming down. Okay. Major cost is because of vacuum and chambers and leak tightness, etc. It is nothing but an electron beam which is generated by a filament which is called electron gun, and they are accelerated by electric fields and focused by magnetic fields, and this beam of electron is made to fall after some collimation using electromagnetic fields, because it is electron, it will listen only to electric and magnetic fields. They are inside a perfect vacuum chamber. So, entire vacuum chamber containing all these magnetic fields, electric fields, electron gun, electron beam and sample, everything is being evacuated by a vacuum pump. And information coming out of it, there will be detectors and screens, etc. That is output. Okay. And then secondary electrons and then X-rays produced out of it. Various things can be analyzed to get various informations. Like SEM is always integrated with another instrumentation called EDAX, which I will show you in the next slide. A scanning electron microscope, the working principle just now I explained, and it produces the images by scanning the surface with electric fields and magnetic fields, so that it goes to various small tiny areas on your surface and give its imaging and give some additional information also. And it is all based on electron diffraction. Okay. Electron diffraction, X-ray diffraction, these are all used to produce images. Okay. Since electron behaves like a wave and its electron wavelength is very small, so the resolution with which electron beam can produce images is very high. So, an electron microscope magnification is very high, more than a lakh, etc. So, you can see very tiny microscopic particles in detail, its physics, its topography, its chemical analysis, everything you can do it using scanning electron microscopy. Okay. And whether such surfaces are acceptable or not, later you can draw some conclusions out of it. So, all this can be done if you do not get monolayer formations, otherwise what you are measuring is not the virgin surface of that material under investigation, some other impure surface. So, you require 10⁻⁷ torr, so that time to form monolayer is long and the electron beam is not deviated, mean free path is very long. So, they will go in the straight line, they will form a beam, etc. They will only be collimated or controlled by electric and magnetic fields. So, turbomolecular pumps backed by dry screw and scroll pumps are routinely being used. And reason for vacuum I have already explained, otherwise the filament that is producing electrons to start with, that will be oxidized, after some time it gets cut like a bulb. Okay. And if the column is having air instead of vacuum, lot of collisions will be there with the electrons and you will lose the beam quality, okay. And it will never reach to the surface. And if vacuum is poor, the residual gas molecules will interact with the surface and thereby you will not get good information on the surface. You will get a blurred image and also you will not get proper chemical information. So, all these precautions if you take, scanning, electron beam, getting diffraction patterns, converting them with suitable instrumentation, okay, by several other instruments, you can get image processing, and these images are very magnified images of a tiny area, unlike optical instruments. So, this is the electron, this is the working principle of electron microscope. And instead of scanning on one side from the surface, if you make the electron beam penetrate through the sample, that is possible if the sample is a very thin sheet. You have to make that sample like that. There are ways to do that. I will not go into details of that because of lack of time. Here idea is to understand the role of vacuum in various types of instruments in a limited time. So, transmission electron microscopy is a technique in which a beam of electrons are transmitted to a specimen to form a transmission image. Okay. It can be considered deflection or diffraction, and finally, it forms an image. Okay. The specimen is most often an ultra thin section of 100 nanometer thick suspended on a grid. An image is formed from the interaction of the electrons with the sample as the beam is transmitted through the specimen, and it is magnified and focused onto a imaging device such as fluorescent screen, a layer of photographic film, or using some sensors such as scintillators attached to charge coupled devices. Finally, you will be measuring signals only, but you have to convert back into images. Okay. So, the things that are coming out are converted into signals, and signals are again processed to produce the imaging. That is called image processing. Now, very good quality advanced image processing protocols have come using very good software programs, and that has to be linked to the entire structure. So, this is the typical column of a scanning electron microscope. Everything is under high vacuum. You can see a lot of vacuum pumps sitting below this, and every such instrument will have very high vacuum pumps attached to that. First, you have to run the pumps, get the vacuum, then only you can do these things, whether it is a SEM or whether it is a TEM. First, you have to get vacuum. If you do not get vacuum, there is no question of scanning electron microscopy or transmission electron microscopy. So, vacuum level is high, and of course, you have to also reduce vibrations. There are ways to do that by connecting it to flexible bellows and some pads, etc. All that you need to do. So, a lot of precautions the operators understand, and they are backed by dry pumps, so that the history of evacuation is very clean right from the atmosphere. So, that is how TEM works. And along with SEM, you can also make an attachment called EDAX. This is another analytical instrumentation, electron dispersive analysis of X-rays. When the electron beam in the scanning electron microscope that I have already discussed, when it strikes the specimen, okay, it can produce images, and you get the image out of that to understand growth at macro level, nano level, whether it is a metallurgical surface or a biological surface, etc. In a micron by micron area, you can get lot of information. That is the physics of it, topography. Okay. But it also, when it goes into that, it excites the sample. Quantum mechanically, lots of orbitals are there, lots of levels are there for the atoms with which the material is made. So, inner electrons are excited by this electron, fast moving electron, and finally again they will jump back into their own orbits. So, several such interactions take place when an electron beam strikes on it, and these X-rays will come out of it, because the excited electrons, excited things, when they come back, they emit X-rays, and this wavelength or intensity of it, that is related to a characteristic of the particular atom from where the X-rays are produced. This physical concept is used because anyway you are having a good electron beam. So, in addition to imaging, why do not you get some information on X-rays produced by the chemical species in the material using the same electron beam. That is how scanning electron microscope and EDAX most of the time they are using a common vacuum chamber, and around 10 power minus 7 to minus 8 are evacuated by modern turbomolecular pumps, etc. And you have to maintain the vibrations levels very small, and you will get very useful information on chemistry of that. It is an investigative method which is widely employed in elemental or chemical characterization of the object. The sample may be of any form, such as solid thin films or powders or liquid sample. It is used in several industries, in aerospace or automotive, or when you develop advanced materials or healthcare management or even semiconductor developments. What you are getting, what is its chemistry, EDAX will tell, what is its structure, physics, the SEM will tell, the grain growth, etc. And of course, you will have to collaborate this, correlate it with X-ray diffraction again, we will see. So, all these analytical instruments are located most of the laboratories in one place. So, that you go with sample and get all those things, SEM, TEM, X-ray diffraction, EDAX, XPS, AFM, mass spectrometry, and then get some information. Then go to another lab where measurements are done, like squid magnetometer for magnetic measurements, or dielectric measurement, or particle analysis, etc., thickness measurement, etc., or oxidation resistance, or particle size analysis. So, with all these things you try to make new material again. This is how research goes on, and if some very good properties are there for that material, that can be correlated with this information coming from these analytical instruments. That is how people do lot of research in most of the advanced laboratories, R&D organizations and industries. Okay. So, the primary component of EDAX is the excitation, which is electron beam coming in the same column anyway, the X-ray detector and pulse processor and analyzer. So, it will analyze the X-rays coming out of it, not the electron diffraction aspect of it, that SEM takes care, or in the TEM takes care. But what is going on here is, in the same time you are getting a parallel information in EDAX. So, while electron diffraction gives images, electron induced characteristic X-rays from the sample gives information on its chemistry. Well, this is not as simple as what I have told. There are a lot of things if you want to get proper information, reliable information in programs and adjustments, etc., and sensitivity analysis and focus to a particular range of masses, etc. All this is a technology by itself, you will get in internet. So, applications of EDAX include assessment of reaction interfaces, characterization of surface defects and residues on metals, glasses, ceramics and polymers, measurement of thickness of layered structures in any microelectronic circuits, etc., layered structures, what is the thickness from this, and there are other spectroscopies like Auger spectroscopy, etc. I am not going into details of all that, but these are all finally related to the interaction of energy and matter basically, whether it is electron or X-ray or electromagnetic interactions. So, electromagnetic interactions, quantum mechanics, atomic physics and electric and magnetic fields, interaction of energy with matter, high speed electrons, high speed ion beams, and in a good vacuum environment, so that monolayer formation is very long. So, all these technologies have to go hand in hand with good software program, which gives out beautiful spectrums and informations, and with some analysis of that also is built in with some softwares like that. So, that way SEM, TEM, EDAX together will give lot of information, but sensitivities vary from point to point. If you want really more sensitive information and very reliable information, X-ray photoelectron spectroscopy is a very powerful tool. You can see the equipment, how it looks like, how complicated it looks like, but a sample will be a small sample sitting somewhere. There is a vacuum pumps here, you see vacuum pump, then another turbomolecular pump, load lock chamber and a magic arm with a magnetic field you put outside, inside the spindle will move, gate walls, and initially preparation chamber of the sample, then it will go inside, degassing should be less, total pressure gauge will give you vacuum levels, and the RGA will give the residual gas environment. After making all that precautions, you try to do something. So, whether it is SEM or TEM, same story here, but it is more stringent requirements here. This is X-ray photoelectron spectroscopy. It is surface sensitive, qualitative technique, spectroscopic technique. Okay. Physicists call it as spectroscopy, sometimes in even chemists, sometimes they call it for chemical analysis, metallurgists and all this, biotechnologists and all, they will treat as a chemical analysis equipment. Okay. So, whoever says in whatever fashion, basically we are trying to understand physics and chemistry of the materials using these matter, using fundamental principles. Okay. So, identify the elements that exist on a material in a elemental level, elemental composition, or covering its surface, mostly surface phenomena. In addition, it gives information about its chemical state, singly ionized or doubly ionized. Chemical states are all, this is a very good information that XPS gives, and what chemical state environment it is there. These are very much required in developing new biotechnological products, enzymes, minerals. When you are trying to do, you want to understand the environment into which several atoms are arranged in different groups, etc., and top of small groups and big groups like that. So, there are ways to do that, that I am not going into detail. And similarly, physicists want electronic structure and density of electronic states of conducting and superconducting and magnetic and dielectric materials, electronic density of states at their Fermi levels and various band structures. That information also can be obtained by X-ray photoelectron spectroscopy. Okay. The main components of an XPS system are a source of X-rays. First you have to produce X-rays like X-ray diffractogram, that will be falling on the samples, and you will get information from various signals coming out of the sample. The details can be understood from the literature where every detail is given, but the main components here are a ultra high vacuum system, a mu metal magnetic shielding, an electron collection lens, because when X-rays fall on it, an electron collection lens, because it is basically a fundamental principle is photoelectric effect. Okay. Einstein has discovered it, photoelectric effect, that has resulted in this instrument. So, when you go into the details horizons, you will get lot of fundamentals there. It is nothing but photons producing some characteristic electrons through which we get information. So, XPS is to get the chemical elemental information compositions. It is not meant for any imaging etc. Okay. So, analyzer, electron energy analyzer, from the energy you can know the binding energies and various other informations, and also the density of electronic states. This is giving another type of information, not just only chemistry or physics. It gives various low, small, still deeper scale information like density of electronic states, chemical state, structure, electronic structure etc. So, sample introduction chamber, sample mounts, all these things you have to understand, and sometimes you may have to heat the sample or cool the sample, and lot of manipulators are there, X, Y, Z and tilt and rotation, so that beams are properly projected etc. Because after all you have to utilize the X-ray beam fully. So, XPS requires ultra high vacuum of 10 power minus 9 torr conditions, although there is lot of research going on to try to shift the things. Okay. Then comes X-ray diffraction, which is a very popular thing. I do not have to explain it in detail at all. It is X-ray diffractometer, since 100 years it is going on. It is basically I have already discussed it when I was discussing in medical applications etc., because it is a simple bulb, electrons coming out of the filament, they hit a copper target, they produce X-rays. These X-rays can be collimated and can go on to a sample, and when they are falling X-rays of a regular arrangement of atoms, there is a constructive interference, and when it constructive interference in integrated manner it comes out, that refracted pattern gives information about arrangement of the atoms or interatomic spacing etc. There is a famous equation, Bragg's equation, 2d sin theta is equal to n lambda. A typical solid state physicists know everything. So, X-rays are generated in a cathode ray tube which is maintained under high vacuum conditions. They are filtered to produce monochromatic radiation, collimated to concentrate and fall on the sample, and it is a scattering process. X-ray diffraction is a very routine process in medical, pharmaceutical, physics, chemistry, everybody uses. The first equipment is X-ray diffractometer. So, use of X-ray RD in pharmaceutical research also is increasing recently. So, lots of companies are manufacturing. In fact, manufacturing X-ray diffraction also can be a good startup. In every university, several academic departments are working on materials research. They utilize the X-ray diffractometer routinely to identify the crystal structure and formation of crystallite sizes etc. Okay. So, X-rays are produced by striking the cathode, that is all, and for which the first Nobel Prize came. So, X-ray producing unit along with other analyzing units, they are all need to be maintained under ultra high vacuum. A small getter is kept inside this X-ray tube to maintain its vacuum, because it is a sealed device. On the spot you do not have a vacuum pump, it is a sealed device, X-rays come out of that. After that it is only collimating them into various things. Okay. Then there is a very important equipment called atomic force microscope. Recently it is coming to know at atomic level the roughness of the surface. Okay. So, atomic force microscope on a nanoscale, it is a very good instrument recently coming. We see how complicated it is. Again it has got lots of vacuum pumps and transfer equipment, main chamber, growth chamber and transfer chamber etc., with lot of analyzers. Everything is based on vacuum technology, and inside you are putting a small sample. What is it you are trying to analyze? Atomic force microscope is a scanning force microscope. a very high resolution type of scanning probe microscopy. How it is done? It is basically a nanoscale tip attached to a small cantilever which forms a spring. As the tip contacts the surface, cantilever bends, and bending is detected using a laser diodes and the split photo detectors. All that instrumentation I am not going to explain. Only thing is the tip sample interaction force, which is atomic force, gives a lot of information about the arrangement of atoms. The major difference here is it does not require any lenses like electric magnetic fields, because it is directly force that you are measuring. And turbomolecular pumps with corn flat flanges and high vacuum chambers need to be used here. So, this is a very sophisticated equipment that is routinely being used nowadays. Then mass spectrometry is a very important spectrometer, which was the starting point of, before all these instruments came, the mass spectrometer was there. I am trying to cover it at the end, because it is the last but not the least. Okay. So, mass spectrometry is an analytical technique by which chemical substances are identified by sorting out gaseous ions in electric and magnetic fields according to mass to charge ratio. It is a sort of getting chemical analysis. It is mostly used in gases and vapors. It can be used in liquids and solids, using some flashing technique and evaporation technique. Finally, the matter which is to be analyzed should be in the form of sort of gaseous type of thing, unlike X-ray diffraction or where specimen can be solid. And there we are interacting with electrons and X-rays, things like that. Here we are interacting ions. Okay. So, we are also getting a chemical information by scanning it by with mass ranges, basically E by M ratio. You can understand these concepts when you go to the discovery of electron and a discovery of neutron, etc. E by M ratio plays a very important role. So, these electrons we are not talking now. Electrons initially will be there, everything starts with electron from a filament that will strike the environment and the gas will be ionized. These ions will be accelerated and they are deflected using magnetic fields, and using the typical force. Magnets always can only deflect the ions. Okay. They cannot accelerate, electric field accelerates, magnetic field only deflects, but deflection is proportional to the E by M ratio type thing. How much is the charge content, what is the mass of it, that is how you get a mass spectrum here. Well, mass spectrometry is a very big phenomena, I can talk hours together. Okay, because we regularly use it in our vacuum technology laboratory and in our superconducting laboratories, etc. A high vacuum system is required for this, a turbomolecular pumping system, a sample handling system through which sample can be introduced, and an ion source, beam of charged particles, characteristic of the samples have to be produced, ions have to be produced. That means, you have to physically evaporate the material type of thing. If it is a vapor, no problem like that, or liquid you have to do convert into ions. An analyzer where the beams are separated according to E by M ratio, and a detector to finally know its state. This is very much used in chemical analysis, and if you lock it to helium, you can use it as a leak detector. What are the applications? Identification of isotopes in chemical elements, determination of their relative abundance, dating of geological samples, impurity analysis in organic and inorganic substances, identification of decomposition products, analysis of unknown materials in chemistry, biology and medicine. So, it is a very useful technique, but when to use this, when to use XPS, when to use EDAX, when to use SEM, TEM, atomic force microscopy, you have to decide. There are Azure spectroscopy, there are many other spectroscopies to know the physics and chemistry of materials. We are treating them as analytical instruments, because all of them commonly use vacuum technology. Well, in the limited time I cannot explain more than that with so many analytical instruments coming up. So, let us conclude. Vacuum based analytical instruments, they are basically analytical, they are essential for characterizing new materials. Research is continuous. See, nowadays every engineering finally is changing its style of work, because new materials are coming. Once upon a time metals, then now composites, they are as strong as metals. So, even in building structures things are changing. So, civil engineering is changing, mechanical engineering, chemical engineering, materials, metallurgy, everything is changing, because new materials are coming. and you cannot bring new materials suddenly without any confidence. So, analytical instruments are very important, and you cannot have analytical instruments without vacuum technology. So, this how vacuum technology is helping us to progress in research in every engineering, okay, to characterize new materials and processes, both physical and chemical processes required for essential needs of mankind. So, modern analytical instruments I already told you in nanotechnology, semiconductor engineering and advanced magnetic and dielectric materials, all these high tech industries they utilize these instruments. Superconducting tapes, ceramics, composite materials, pharmaceuticals, basically to understand physical and chemistry of it, and their products will be solids or liquids or gaseous forms. Okay. So, to do some new things you require these things. So, X-ray diffraction gives crystallinity information, same time EDAX give morphology and chemistry of surfaces and interfaces, XPS gives detailed chemical analysis with high resolution, AFM gives atomic arrangement at nanoscale, and mass spectrometry gives relative abundance of elements in the sample. But ultra high vacuum is the backbone for all these analytical instruments. The vacuum chambers, gauges, leak detectors of high quality are necessary to realize modern analytical instruments used in various fields of science and technology. So, in every institute or R&D organization or industry, we need vacuum pumps, we need vacuum technology, we need vacuum experts to take care of various industrial products. So, that way I can tell you vacuum technology plays a very important role in analytical instruments. Thank you.